Greetings to you. You are welcome to the third class of our lectures on elementary differential equations. So in this video, we are going to consider the solution of differential equations. Before we start, I'll first of all present to you the concept of family of curves, and I will bring the idea of integration to explain this concept to you. Then thereafter, I will explain to you the meaning of general solution, particular solution, and singular solution. And thereafter, I will give you a typical case of a particular first order differential equation whereby we have a solution, but the solution is discontinuous at a point, and I will use that one to bring to your attention another concept of solution of differential equations. Now let us consider first order linear differential equation. As you can see on the screen, if you look at this problem, it's very simple, because what we are trying to say is that the rate at which y is changing with respect to x is 3, and which means that m there is the rate of change, and you can even say that 3 is the gradient in that particular differential equation. So let's rearrange. By the time we rearrange, we see that the y is equal to 3 the x. So let us integrate both sides. We'll see that. Then the next thing we are going to do now is that we have integral dy is equal to integral 3 dx. Don't forget that if you integrate y, if you integrate dy, what you have? You have y. If you integrate 3 dx, what you have? You have 3x. Don't forget that there's x is per 0 there. Okay? Then there will be a constant of integration, isn't it? Okay? Now, don't forget that c is the constant of integration. So let's proceed now. Now, the next thing is that let's use this expression to come up with a table. Look at the table now. In this table, you will notice that when c is 8, when the constant of integration is 8, I will have y is equal to 3x plus 8. Then if you put x here, don't forget in secondary school, you have this expression. Then as well, when c is 3, you have 3x plus 3. Then you have this expression. Then when c is 0, you have 3x. Then at the same time, when c is minus 10, you have this expression. You cannot see now that here we're having 4 different lines. Why are we having different lines? Because we are trying to vary the constant of integration. That is exactly the genesis of family of curves. There's no way you talk about family of curves in differential equation and you won't talk about the constant of integration. That is the genesis of it. Now let's take a look at it now. So if we know now that y is equal to 3x plus c, now let's look at the diagram we have here. You see that we have all those lines there. We have 4 lines. That's not all. Let's proceed now. This, what we have here, it represents a family of curves. And at the same time, each of the curves in the family depend on the value of c, which I've explained to you before. It is the c that will let us know the nature of the line. But don't forget that all of them, we obtain them using this expression y is equal to 3x plus 3 plus c. Now, each of them, they're actually straight lines. And all of them have in common is that the gradient of each line is 3. The gradient of each line is 3. Now, we cannot say that a particular curve of a family may be determined when a point on the curve is specified. Now, in this case now, all of them here, they are the solutions of a differential equation, dy dx is 3. So if all of them are the solutions of dy dx is 3, then which of them is the exact solution? We need to be specific. We need to be specific. Now, there are many lines, as you can see. In fact, I even show you just only 4. We have infinitely many solutions. That's why we say it in differential equation. We said we have infinitely many solutions. But out of them, we need to be specific and pick one. Then how do we need to be specific? In that case, we need to mention a particular point that the line must pass through it. So that is how to be specific. Now let's consider that the point is 1, 2. So if the point is 1, 2, then this implies that x naught is 1, then y naught is 2. Don't forget in Cartesian. In Cartesian, we have s, y. So just like we have in Cartesian, we have s, y, definitely likewise, we have x naught, y naught there. So we are going to substitute all this back to the expression so that we can find our c. Now look at the expression again. Then I've changed y to y naught. I've changed my x to x naught. So I have this. So if you substitute 2 and 1, you will see that we can obtain our C to be minus 1. So if you obtain our C to be minus 1, what is the next thing? We substitute back to the problem. Then we now say that the final solution is 3x minus 1. Don't forget, see, by the time we get to the last slide, I will still explain to you how we are going to call this one particular and general solution. See, if you look at this now, in this problem now, we already have a general solution, we already have a particular solution, but when we get to the definition of term, I'll bring to you the exact meaning. Example 2, dy dx is equals to 4x, and in this case we have y of 2 to be 3. Now you will notice that here I've been so good enough to specify the point, and the point here is 2, 3. Okay, so let's continue now. So the question now is this: we are asked to sketch the family of curves given by equation 1 below and determine the equation of one of these curves which passes through the point 2, 3. Okay, so let's continue. The first thing we're going to do is that we need to integrate both sides of the problem. If we integrate both sides, we have this. So what is the next thing again? We have, if you integrate dy, you have y. Then if you integrate 4x, you have, don't forget, if you integrate 4x, you have 4x raised to the power 2 divided by 2. Then 2 we cancel 4, we give you 2. Okay, then we have c, which is the constant of integration. So how do we get c now? We need to use the point 2, 3. So if you use point 2, 3, then you have this expression. So from here we can see that our c is something we know to be minus 5. Don't forget that 2 square is 4. 2 square is 4. Then 4 times 2 is 8. Then if 8 should go to the other side, it will be 3 minus 8. That will give us minus 5. So that means that the constant is what? Is minus 5. So with that now, we can now plot the graph of this one. Don't forget that here, this is an example of a quadratic equation. So we can see now that there are many curves here. So here, that is when, in this case now, this graph here, we have plus 15. But that is when c is 15, when c is 8, when c is 0, when c is minus 6. So this is what we refer to as the family. Next is for us to test for the solutions. The two problems that we solved before, we are going to consider the same problem again, then we test the solution we have. Let's consider the first slide, as you can see there. Now, let's say we have y of 1 is equals to 2, and for the second we are using y of 2 is equals to 3. So let's differentiate both sides. Then if you differentiate both sides, you notice that in the first side we have y is equal to 3x plus c. In the second one we have y equals to 2x squared plus c. I don't need to explain this. I've just shown you how to obtain this now. Now, if we use the two constants, you will notice that 3x minus 1 is the correct solution for the first one. And for the second one, y is equal to 2x squared minus 5 is the solution. Then the next thing now is that let us substitute the solution back to the problem. If you substitute the solution back to the problem, you notice that if you differentiate the both sides, you see that what we have is exactly the same problem. So what does that mean? That one is to let us know that indeed the two answers we have in blue colors, they are the correct solution. What does that mean? Once again, the two answers we have there, the two solutions, they are indeed the solution. But don't forget, the next thing we are now going to know is that what do we know as general solution? What do we know as particular solution? So I will use this concept to explain the two. But note that it is normally a simple task to verify that a given function, which is the solution, satisfies its differential equation. It's very normal. Please, it's very normal. All you just have to do is to bring the function, you take it back to the problem, and you see that it's satisfied. Now, definition of terms. A real or complex value function that is defined on an interval is called a solution or an integral of the differential equation. What do I mean by that? Let's say we have a differential equation like you can see on the screen. This one is nth derivative. It has n derivative there. Then we are sure that phi of x that we call the solution, it must have n time differentiable. I mean, what I'm trying to say is that anything we come up with at the solution, let's say we are dealing with second order now. Let's say we are dealing with second order. Then it means that the solution, we can differentiate it twice. Let's say we are dealing with fifth order. The solution, we must be able to differentiate that solution 5 times. If you are dealing with seventh order ordinary differential equation, it means that the solution, we can differentiate it 7 times. That is what we mean by the solution is n time differentiable. And then the next condition is that the independent solution, the first derivative of the solution itself, the first derivative up to the n derivative, they must satisfy the equation. So that is what we mean by solution. But there is one thing we need to notice here now. A solution can be real and it can be complex. So a solution of ODE could be real. That is if the solution is indeed a real function. It could be complex if the solution is complex. For instance, like the one you can see in your lecture note, that way we have the solution to be c then exponential ix. In that case, I is square root of -1. And that one is what we are talking about there. So whenever you have a solution and your solution, you can see something like I. That means that even when you are dealing with cos and sine, don't forget that cos and sine too, they have this exponential function there. Okay, and then it's very possible for us to have I there. So when we have the I there, then we call it a complex valued. So in the first case, if it's a real solution, then it means that the y, which is the solution, must have a real function. And if it is y, if y is complex, then it means that the solution must be a complex function. Now let's consider this example now. We are to show that any constant c, the function which is c exponential x, is the solution of the problem we have of the board. Look at it here. We say that x belongs to a real number. That means that x could be -5, it could be +5, x could be -100, it could be +100. That is what we mean by x belongs to a real number. So we have this as a problem now. We want to check that this is indeed the solution to this. So we are still on the testing method. Now, let's put it down here. If you put here, I only replace my y with c exponential x. So if you differentiate this one, don't forget that how do you differentiate exponential x? You differentiate the power x, you have 1, you multiply 1 by the numerator, you multiply 1, then you have this problem. So if you differentiate c exponential x, you see have c exponential x. And if you look at c exponential, you do know it's the same thing as y. So what does that mean? It means that y of x is equal to c exponential x is indeed a solution to the problem. That is what we are trying to say here. Now let's go to example 4. In example 4 here, we have 2 different solutions. Solution 1 is y of x. Solution 2 is z of x. And both of them, they have different contents. Look at the first one. It has a cos 2x, while the second one has b sin 2x. And we are asked to show that each of them is a solution to this particular problem, provided that x belongs to a real number. Let's start with y. If we differentiate y, which is a cos 2x, what do you have? You have -2a sin 2x. Please don't forget how to differentiate sine and cos. Please, I will advise you. Don't forget that if you differentiate sine, you have what? You have cos. If you differentiate cos, you have what? Minus sine. So if you differentiate cos, if you differentiate a cos 2x, what we have is -2a sin 2x. So if you proceed again and you differentiate the second time, you will see that you have -4, then a cos 2x. So let's substitute everything back to the problem. Then we substitute back. This is my second derivative. Then this is my 4 multiplied by y. Do you notice that is equal to 0? Then what does that mean? It means that a cos 2x is a solution to the problem. So we can't stop there. Let's consider and use z again. If we use z, now look at it now. We now have z is equals to b sin 2x. So here, our task now is to substitute this one into the problem to test if it's indeed a solution. But don't forget that before we could proceed, we need to differentiate it twice. So if you do the first derivative, you will see that 2b cos 2x. If you do the second derivative again, you see that you have -4b sin 2x. Then if you substitute into the problem, then you see that it is indeed equals to 0. So what does that mean? It means that b sine 2x is a solution. So does that mean we have two solutions? That is the point. Now, one thing I will now advise you is this. We have what is called linear solution. We have what we call a multiple solution. In this case now, solution 1 and solution 2. If we add them together, you will notice that it is also a solution. So you can take your biro to check. In this case, k of x is the solution, is the addition of the two solutions. Then if you add them together, you will see that it will give you a perfect solution. But there is something I'm not saying here. There is something. And that one will still lead us to what we call linear dependency and linear independent solution. I will still discuss that one with you later. But if you look at this one now, what we are trying to say is that if a cos 2x is the solution, if b sine 2x is the solution,
the next thing we're going to consider now is the definition of general, particular, and the singular solution. As we can see on the screen, the general solution is the solution of a differential equation in which there is a constant in it. Let's consider example 1. Example 1 here, we can see clearly now that 3x plus c is the general solution of the y dx equals 3. You remember this problem that we've solved it before. Exactly, we've solved the problem before. So another one is example 2. Here in this example, you can see now that y of x equals to a cos 2x plus b sine 2x is exactly the general solution of 2x squared d square y dx squared plus 4y equals to 0. But most important thing is that if you look at the first order and second order, if you look at the solution, you see the constant of integration there. You will see constant. That is exactly what we are trying to say, that whenever we are talking about the general solution, there will be a constant in the solution.
The next thing we are going to talk about now is called particular solution. Any solution which is obtained from the general solution by giving particular values to the arbitrary constant is called a particular solution. In this case, what we are trying to say is that any solution that we are talking about in such a way that we specify the point that the function will pass through, that is what we are referring to as exactly a particular solution. For instance, now let's take a look at example 1, that is the y dx is equals to 3. You see that in this case, we've been able to use the constant of, we specify the line, that the curve, that the line must pass through, and we're able to obtain this expression here as the equation of the straight line. In that case, though, we know the intercept, y-intercept, okay? So, and at the same time, let's take a look at the second one again, the second derivative again, the second order ordinary differential equation. In this example 2, yx equals to 1 cos 2x plus 2 sin 2x is the particular solution. You will notice that in this case, we already know our a and b. And how can we get our a and b? We can use the initial condition. And that is how we obtain this. So we call this one particular solution. And one thing we should notice here is that in the case of particular solution, there is no constant. There is no constant at all in the solution.
Another definition we are going to consider now is called singular solution. In this case, it's a kind of problem, it's a kind of solution of a differential equation in such a way that we know the particular solution, we know the general solution, but we may find it very, very difficult to obtain, in the sense that, let me explain better now. We call this one a solution of a given differential equation which cannot be obtained by assigning a definite value to the constant in the general solution. Now, if you look at this first order, second degree ordinary differential equation, you will notice that here, if you take a look at this general solution, you will notice that it's the solution to the problem. Fine. And if you look at the particular solution, you will notice that this particular solution, it does not contain any constant. Why the general solution contain constant c, and both of them, they are the solution. But if you look at the second one, you notice that it's very challenging for us to obtain particular solution from the general solution. There is no value of c that we can substitute in the general solution that can give us the particular solution. This kind of solution is what we call singular. The last thing we are going to consider now is the case of no solution. Let us consider the differential equation dy dx is equal to f of x, where f of x is 0 and 1, and then the ranges are specified. The question is this: does the solution y of x of the differential equation exist for x belongs to real number? Now, let me explain this to you better. In this case of real number, we're talking of from minus infinity to plus infinity. And from minus infinity to plus infinity, zero is included. We have from, let's say, minus 3, minus 2, minus 1, 0, 1, 2, 3. So zero is included. But the question now is this: does the solution y of x of the differential equation exist for x belongs to real number? It's very simple. Let me explain to you now. Let's consider the first part now. When dy dx is 0, for x is less than 0. If you cross multiply and you integrate, you will agree with me now that y of x is equal to c, because it is only c that you can differentiate and you have 0. Even if you agree with me, let's come back here. Let's differentiate y of x, you have dy dx. Let's differentiate c, you have 0. Then you have this expression. Now, let's go to the second aspect now. That is when dy dx is equal to 1 for x is greater than 0. Now, if you look at this again now, you will notice that if you cross multiply, we have dy is equal to dx. By the time we integrate, we have y of x is equal to x plus c for x greater than 0. Now, in this case, you will now see that we've been able to have the two likely solutions. We've obtained the two solutions. So let's now go ahead now to check. There's number one thing we need to notice. The first solution, y of x, the second solution, x plus c, they satisfy the differential equation perfectly. Substitute, you see that y of x equals to c, y of x equals to x plus c, they are the solutions of the differential equation. But you notice that there's a problem. At x is equals to 0, we don't know anything about the solution. And x equals 0 is included in the real number. Number 2. That means that the solution y of x we are talking about, it is discontinuous at x equals to 0. Number 3. Thus, we can say now that the differential equation has no valid solution for x equals to 0. However, y of x is defined above is the solution of the given differential equation at all points other than at s equals to 0. So which means that in this case now, there is no solution at s equals to 0. So we're going to stop here. Thank you very much. Thank you for listening.